Welcome! In this video I talk about functions in Rust. Functions are central to the whole language, in particular because the way arguments are passed into functions and return values are passed out of functions is instrumental for borrow checking and the concept of ownership. Therefore, I can in this video talk about these concepts as well. We start with a small example. I've set up a project and my main file contains a single function and the main function. Here you can see how the function f is both defined up here and called down here, so this is pretty much unsurprising. If I run this, I first see hello world, then I see hello from f, and indeed in the main function we first print hello world, and then we call the function and print hello from f. Now let's look at a function argument. Let me pass in a string to the function. Here I declare that the function gets as one argument the value s of type string. I can use it in the function to print it, and I can hand it in this way. Notice that string is an ownership type, so it owns the memory it allocates, and ownership of the string is transferred into the function by this notation. Let me see how this works. I've handed in the string ABC and it is printed within the function f. Let me try to underline this point by trying to use the string after the function call here. If I just print something here and try to access the string variable, then the compiler is not at all happy with me. So I can see this here in the VI, but if I move to the things, it says to me, borrow of moved value st. Value borrowed here after move. So from a C++ standpoint, this means the value of the variable st has been moved into the function and is no longer available outside. Yeah. If I compile this, I get a very long message saying that the move occurs because I have a type string here. It has been moved into the function when I called f, and when I later try to access it outside, I need a borrow, we'll talk about this later, after the move, and so the compiler won't let this pass. There's even hints, I could clone the string or whatever, but the string argument here takes ownership of the value which is handed in. Let's see how we can circumvent this problem in case we actually need the string outside again. We can make this argument not a string value type, but a reference to a string. And we can then hand in here a reference to st, which means I can later use the value. So let's see whether this builds and runs. This does exactly what you expect. Let me explain. The type here is a reference to string, an immutable reference to a string, which is handed in here. So I have to give at the call side, I have to give the ampersand to say it's a reference, an immutable reference. And that means that the value stays outside here. It's only a reference which is in the function, and therefore I can happily use it after the function call. Now what if I have to mutate the value within the function? Well, I can hand in a mutable reference. That's written like this. And then I have to hand in a mutable reference. And that means that in the function, I can do something like push string and append something, let's say xyz. And now it's not happy with me. Because it's an immutable variable, I have to make the variable mutable. And then I can hand in a mutable reference, can mutate it within the function, and can use it outside again with the changed value. Let's try to see what happens if I run this. Indeed, inside the function, the string value is ABC, and outside I see ABC xyz because xyz has been appended within the function. Let me try to explain the borrowing rules of Rust with a small example. This is essentially what we had, except that I outside when I return from the function, I create additional immutable references to the same string variable. And this program runs and does what you expect it to do. It writes 3 times the value ABC XYZ. But let me explain why this is allowed. So first of all, the compiler looks at the usage pattern of this variable and sees that it needs a mutable reference for the function call, but after the function call, it only needs st immutably. Therefore, it can say, that's okay, there is a single mutable reference here, but once this has expired, the function has returned, there can be multiple immutable references, because that is exactly the rule. There must always ever only be one mutable reference to a value, or there can be multiple immutable references. So the fact that the compiler notices that st might be mutated within the function, but is not mutated after the function call here, allows the borrow checker to say it's okay to have here 3 references, a, b, and the one needed for this st printing here, which are immutable, and so the rule is fine. Whereas when I hand the mutable reference into the function, there is at this time only one available. Let's do another example. In this program, again slightly modified, I again hand a mutable reference into the function, I mutate the string. Then I get an immutable reference, a, to print it here. And then I get another mutable reference, b, to print the value again. Now the compiler can analyze that neither st nor a are used down here between the definition of the mutable reference and b itself. So therefore, the rule is okay. There's only one mutable reference being used at a time. And indeed, this program builds and runs fine. Now let's look at return values. In this example, I change the notation of the function such that it takes a mutable reference, mutates the string, and then returns a different string. Notice that I have here used the syntax that here I give the return value, and if the last expression in the function is not terminated by a semicolon, that means the last expression computes something which is then returned as the value of the function. Returning is moved by default as well, and therefore this program here, which declares t to be the return value of f, works, and if I ask for the type of f, which is here automatically determined, it's just string. So the string st is modified here, and then again a new string is computed, which is returned and stored into this variable by means of move semantics. And then I can print both, and if I run this, then you see the two values abc xyz and abc xyz abc. This was it for this video. I cannot hope to have explained the full depth of borrow checking, ownership and everything of Rust, but I think I have given an idea of what's going on and what the borrow checker is for as a first impression. Thanks for watching. See you in the next video.